Complex megaprojects represent the zenith of engineering ambition and intricacy, embodying challenges that extend far beyond mere size or cost. These monumental endeavors intertwine multifaceted technical systems, interdisciplinary expertise, evolving stakeholder interests, and unpredictable environmental and social dynamics, crafting infrastructures whose scales and complexities redefine human capability. This in-depth exploration embarks on a comprehensive investigation into the world's most complex megaprojects, exposing the profound layers of engineering innovation, strategic management, and adaptive problem-solving that drive their realization. Complexity in megaprojects arises from multiple interwoven factors. The sheer scale of physical construction mingled with intricate interdependencies among diverse systems, sophisticated interplay between technological innovation and site-specific conditions, extended timelines overlapping shifting economic, political, and community contexts, and the imperative to harmonize sustainability and social responsibility with performance and safety. These projects challenge linear construction paradigms, demanding flexible, integrated approaches operating within uncertainty and dynamic constraints. One illuminating example is the Crossrail project in London, officially known as the Elizabeth Line, spanning over 100 kilometers, including 42 kilometers of new tunnels under dense urban fabric. It integrates new underground rail tunnels with existing surface lines, necessitating intricate coordination of civil engineering, rail systems, signaling, ventilation, and power supply across fragmented infrastructure. The project navigates heterogeneous geology, clay, chalk, water-bearing gravel beds, requiring variable tunneling approaches from earth, pressure-balanced TBMs to sequential excavation methods. Complex station excavations involve multidisciplinary coordination, harmonizing architectural aesthetics, passenger flow engineering, safety, and accessibility within constrained sites, bristling with utilities. Supply chains stretch globally, sourcing precision rail components, signaling technology units, and vast quantities of bespoke concrete linings. Integration of new digital signaling with legacy systems mandates comprehensive testing and validation under tight reliability thresholds. The significance of Crossrail transcends engineering, enhancing regional connectivity, economic vitality, and urban regeneration, inseparable from its complexity. Another paragon of complexity absolute is the ITER, International Thermonuclear Experimental Reactor, megaproject near Cadarache, France. This international collaboration among 35 nations aims to master nuclear fusion for sustainable energy. The engineering challenges are staggering. Designing a tokamak, a donut-shaped plasma containment device, operating at temperatures exceeding 150 million degrees Celsius, with magnetic fields 100,000 times the Earth's magnetic intensity to confine plasma. Hundreds of specialized superconducting magnets, constructed from niobium tin alloys, must be manufactured with nanometer precision and assembled within sterile cleanrooms. Cryogenic systems maintain magnet cooling near absolute zero. Remote handling systems execute maintenance in high radiation environments. Control systems manage complex plasma instabilities, harnessing petabytes of real-time sensor data. Construction demands coordination across continents, with component fabrication, shipment, and assembly involving exacting tolerances and schedule synchronization. ITER embodies humankind's most complex engineering system, endeavoring to replicate the power of the sun on Earth. In the context of urbanism, the Hong Kong-Zhuhai-Macau Bridge contains multiple complexity layers reflecting its audacious scale and challenging environment. Stretching 55 kilometers over the South China Sea, it combines bridges, artificial islands, and a 6.7 kilometer immersed tunnel navigating heavy marine traffic corridors and typhoon exposure. Submerged tunnel construction involved sinking massive precast concrete elements into dredged trenches with intricate grouting and watertight sealing undertaken beneath turbid, high-pressure waters. Bridges employ innovative aerodynamic design to resist typhoon winds and seismic forces while minimizing environmental footprints. The project required seamless coordination across jurisdictions involving distinctive political, regulatory, and cultural frameworks, compounding technical complexity. Environmental protection demanded mitigation of coral reef disruption and marine habitat preservation amidst massive reclamation activities. Engineering complexity in megaprojects also extends into the integration of enormous digital and control systems. The International Space Station, a marvel of orbital engineering, epitomizes persistent system complexity, interconnecting modules fabricated in different countries, operating under continuously evolving configurations and stringent safety regimes in microgravity and space radiation environments. The station handles power generation from expansive solar arrays, life support recycling systems, and scientific instrumentation, requiring redundant and fault-tolerant avionics. Assembly conducted through multiple shuttle missions and spacewalks demanded extraordinary logistics and precision. Megaproject complexity translates into risk profiles characterized by high uncertainty and interrelated risk factors, including technical failures, cascading into schedule delays, cost escalations, or societal opposition. Complexity management utilizes systems engineering methodologies, establishing requirement traceability, interface control documents, and multi-layer verification hierarchies to tame risks and ensure coherence. Agile project delivery principles, adapted to mega-project scale, promote iterative progress and stakeholder feedback integration, facing shifting parameters. Supply chain complexity spans globally distributed manufacturing and procurement networks, requiring meticulous logistics planning, accounting for cross-border customs, transport modes, component synchronization, and quality control, coupled with resilience planning against geopolitical shocks and raw material volatility. Environmental complexity emerges as mega-project footprints interact with diverse ecosystems, necessitating robust impact assessments, biodiversity protection plans, and sustainability innovations embedded within civil and structural designs, integrating nature-based solutions alongside hard infrastructure, enhancing ecological connectivity and climate adaptation. Social complexity surfaces from navigating multiple stakeholder interests. Governments, indigenous communities, local residents, investors, NGOs, and end users, involving transparent governance, community engagement, grievance redressal mechanisms, and equitable benefit sharing, ensuring social license and ethical stewardship. Human resource complexity manifests in coordinating large, culturally diverse workforces with variant skill levels, requiring adaptive training, safe work practices, and team cohesion policies essential under dynamic and high-risk conditions. Megaproject lifecycle complexity spans decades, demanding phased financing, technology evolution management, regulatory compliance adaptation, and comprehensive knowledge capture, securing continuity through personnel transitions and organizational learning. Technology complexity arises with emerging tools, digital twins, AI-enabled design, advanced construction robotics, transforming traditional workflows into integrated cyber-physical systems, facilitating smart monitoring, predictive maintenance, and operational optimization. In aggregate, complex megaprojects mediate profound synthesis among engineering science, management acumen, socio-environmental responsibility, and technological innovation, demanding unparalleled collaboration, foresight, and systemic orchestration. This series embarks on unraveling this multifaceted complexity, by dissecting exemplary megaprojects, thematic challenges, and transformative engineering approaches illuminating the human ingenuity, enabling the monumentally complex infrastructures shaping contemporary and future civilization. Tunneling megaprojects encapsulate a pinnacle of complexity within mega engineering, threading vital transportation, utility, and industrial arteries beneath challenging terrain, urban centers, and aquatic expanses. The multifarious technical, environmental, and managerial demands inherent in these subterranean colossi typify engineering systems where uncertainty, scale, and stakeholder convergence interplay dynamically, compelling innovative solutions and adaptive strategies at every project phase. One of the most striking examples is the Gotthard Base Tunnel in Switzerland, a masterpiece of alpine tunneling engineering extending 57 kilometers through the rugged Central Alps. Its construction confronted daunting geological adversity, penetrating deeply metamorphosed crystalline rock interspersed with fault zones, high geothermal gradients, and high rock stress fields. Comprehensive geotechnical investigations, including core drilling, geophysical imaging, and in situ stress measurements, informed the design of varied excavation and support methods, ranging from traditional drill and blast sequences to mechanically excavated sections using earth pressure balanced tunnel boring machines, EPB TBMs. The precision required to maintain alignment within mere centimeters over such length reflects an extraordinary orchestration of surveying technology, real-time data feedback, and interdisciplinary collaboration. Logistics Solutions coordinated the continuous removal of excavated muck, transport of support materials, and worker rotation through multiple gallery access points, optimizing progress rates while maintaining stringent safety. Safety considerations impose rigorous requirements given the tunnel's length and isolation, necessitating compartmentalized fire safety zones, emergency egress galleries, and bidirectional telemetry communication systems ensuring effective evacuation strategies in emergencies. The project integrated state-of-the-art structural health monitoring, employing fiber optic sensors embedded within shotcrete linings, assessing deformation, moisture migration, and microseismic activity, facilitating condition-based maintenance and risk reduction. Environmental stewardship mandated controlling groundwater inflows, managing sediment transport affecting alpine streams and lakes, and restoring surface habitats post-excavation, preserving biodiversity hotspots intrinsic to the region's ecological fabric. The Channel Tunnel, connecting the United Kingdom with France beneath the English Channel, epitomizes maritime tunneling complexity. This 50-kilometer undersea tunnel demanded excavation through variable chalk marl strata beneath a busy shipping lane with sea depths up to 40 meters. The intricate geotechnical conditions necessitated combined use of slurry shield and earth pressure balance TBMs, supported by an exhaustive ground conditioning program employing bentonite slurries, stabilizing the excavation face under hydrostatic pressure. A unique feature was the construction of twin rail tunnels flanking a central service tunnel, requiring precise spatial coordination and sequential excavation methodology, minimizing risks of ground settlement or water ingress affecting adjacent port urban infrastructure. The erection of tunnel lining utilized modular segmental precast concrete rings balanced for durability against chloride ingress and marine corrosion with advanced water-stopping seals, ensuring structural integrity. Ventilation and safety systems incorporated mechanical air circulation, emergency refuge chambers, and rapid incident response coordination enabling safe and reliable operation. Urban tunneling megaprojects, such as New York's East Side Access Project, push complexity within dense civic confines. This vast endeavor connects Long Island Railroad LIRR to Grand Central Terminal, through excavations beneath historic districts saturated with utilities, subway lines, and geological variability from soft sedimentary sequences to bedrock outcrops. Ground freezing, jet grouting, and compensation grouting stabilizations mitigate settlement risks, preserving building foundations and transport networks overhead. Maintaining uninterrupted metro and rail services throughout construction demanded layered scheduling and construction phasing, integrating shield tunneling, cut and cover techniques in mine station caverns with dust, noise, and vibration abatement, minimizing community disruption. The project integrates advanced tunnel boring machines augmented by real-time sensor feedback tracking, cutter head torque, machine thrust, and ground conditions, optimizing excavation performance and minimizing downtime. Complex dewatering schemes combine well point systems and deep pumping stations, preserving underground water tables critical to urban equilibrium. Emergent tunneling technologies underpin these megaprojects' escalating ambitions. Tunnel boring machines with customizable cutter heads adapt seamlessly to mixed face conditions. Intelligent machine control automates steering and parameters adjusting for rock variability. Slurry recycling systems enhance environmental compliance. Reducing waste, segment erection automation with robotic handling increases precision and worker safety. Digital twin models replicate the complete tunneling system encompassing mechanical, electrical, and civil components, enabling predictive maintenance and scenario testing prior to physical intervention. Cross-disciplinary integration remains essential. Civil, geotechnical, mechanical, electrical, and environmental engineers collaborate closely with geologists, hydrologists, urban planners, and sociologists to harmonize excavation techniques, ground support systems, sanitary and ventilation designs, safety protocols, and community relations. Multinational contractor consortia and supply networks orchestrate complex logistics underpinning timely delivery of raw materials, tunneling segments, and specialized equipment under variable regulatory regimes and geopolitical landscapes. Environmental management embraces mitigation of biodiversity, disruption, sediment transport alteration, groundwater quality preservation, and air emissions control during muck handling and machinery operation. Social impact frameworks incorporate transparent consultation, equitable compensation, and disruption minimization, fostering coexistence between urban populations and monumental underground infrastructures. In summary, tunneling megaprojects represent complex systems marrying sophisticated technology, adaptive engineering methodologies, systemic risk management, and social environmental governance to carve indispensable subterranean corridors, facilitating mobility, utility access, and economic vitality on global scales. Their realization exemplifies the zenith of human ingenuity and cooperative endeavor, confronting natural and social complexities beneath the surface of modernity. Complex bridge megaprojects stand as iconic testaments to engineering mastery, simultaneously confronting the formidable forces of nature and the exacting demands of global connectivity within intricate socio-political and environmental contexts. These monumental structures transcend the straightforward span of rivers or valleys, integrating cutting-edge materials, advanced structural concepts, and multifaceted systems underpinned by unprecedented logistical organization and risk governance. The structural complexity inherent in long-span bridges stems from intricate load transfer mechanisms necessitating innovative design approaches sensitive to aerodynamic, seismic, thermal, and fatigue effects. The Akashi Kaikyo Bridge in Japan, for instance, boasts the world's longest central span at 1,991 meters within a suspension bridge system engineered to withstand frequent typhoons and seismic events along the Japan Trench Fault line. The main cables, comprising tens of thousands of galvanized steel wires braided into robust bundles, must endure tensile forces exceeding 40,000 kN/s, while maintaining elasticity to absorb dynamic excitations from wind and traffic. Anchorages founded into granite bedrock employ post-tensioning techniques ensuring stability over a century service life. Detailed wind tunnel testing, computational fluid dynamics, CFD simulations, and aeroelastic modeling informed the deck shape design, minimizing vortex-induced vibrations, and aeroelastic flutter, a pioneering integration of fluid dynamics and structural mechanics. The construction logistics of Akashi Kaikyo involved multifaceted marine and aerial operations, orchestrating synchronized erection of towers rising over 300 meters, spinning of cables from deck to anchorage points, spanning shipping lanes, and segmental deck launching over open water utilizing catamarans and advanced tensioning systems. Precision alignment activities maintained millimeter-level tolerances critical to the suspension system's integrity. Implementation of health monitoring systems employing accelerometers, strain gauges, and GPS ensures continuous dynamic tracking, aiding in proactive maintenance and structural health evaluation. Similarly, the Millau Viaduct in France, a cable-stayed bridge soaring 343 meters over the Tarn River Valley, melds structural slenderness with breathtaking aesthetics and resilience. The pre-stressed concrete pylons ascend like spires resistant to wind loads through aerodynamic shaping and cross-sectional optimization. Cable stays composed of parallel strands provide lateral and vertical support, distributing deck loads dynamically during traffic fluctuations and seismic events. The incremental launching construction technique propelled the deck from valley sides, employing hydraulic jacks controlling progress and alignment, meticulously avoiding bearing stresses, surpassing design limits. Detailed soil structure interaction modeling accounted for complex limestone substrata variability, ensuring foundation stability over multi-century horizons. Material innovations underpinning these bridges include ultra-high-strength concretes and corrosion-resistant alloys, augmenting durability amid corrosive coastal environments, while enabling reduced cross-sectional sizes and structural weight. Use of fiber-reinforced polymers, FRP, in protections and reinforcements enhances fatigue resistance and facilitates longer inspection intervals. Environmental complexities command mitigation strategies, addressing ecological sensitivities. The Hong Kong-Zhuhai-Macau Bridge Complex, a transoceanic megabridge extending over 55 kilometers, includes immersed tunnels, artificial islands, and viaducts constructed respecting marine biodiversity, including coral reefs and fisheries. Construction phases embodied environmental risk assessments and ecological compensation, including reef translocation and habitat restoration. Sediment plumes control technologies and pile driving noise suppression techniques minimized marine disturbance. Coordinated multi-jurisdictional environmental monitoring ensured compliance across the politically unique Greater Bay Area. Complex bridge megaprojects also encapsulate urban integration challenges. The Beijing Grand Bridge, part of the Beijing-Shanghai high-speed rail, traverses densely populated zones requiring precision in noise, vibration control, and land acquisition management, alongside dynamic traffic and community engagement. Techniques such as vibration isolators and sound barriers blend engineering rigor with public health considerations. Risk management integrates multi-hazard resilience against natural disasters, including typhoons, earthquakes, and tsunamis. Redundancy in critical structural elements. Base isolation systems and dissipation devices enhance survival, while structural health monitoring networks provide continuous data streams, employing machine learning anomaly detection, augmenting human inspection. Financial and contractual complexities arise from the scale and novelty of engineering technologies, demanding sophisticated procurement frameworks. Alliances between public bodies, international engineering firms, and local contractors balance design innovation with regulatory compliance and stakeholder interests. Digital transformation embeds digital twins, enabling virtual construction rehearsal, real-time condition monitoring, and predictive maintenance forecasting, a paradigm shift in life cycle management, optimizing performance and cost. These bridges exemplify human ingenuity, converting natural obstacles into conduits of prosperity, each megaproject a confluence of art, science, management, and diplomacy, reshaping landscapes physically and symbolically. By understanding the intricate layers of design, construction, logistics, environmental stewardship, and governance, embodied in bridge megaprojects, engineers and societies glimpse the profound complexity and achievement committed to sustainable infrastructure futures, enabling unbounded connectivity. Ultra-complex high-rise megaprojects redefine vertical engineering through unprecedented height, layered functionality, and integrated sustainability amidst ever-tightening urban footprints. These towering structures represent multi-dimensional challenges, combining structural innovation, advanced material systems, cutting-edge vertical transportation, and holistic environmental integration. Examining the confluence of these factors reveals how engineering continuously pushes the limits of technical, architectural, and operational complexity. Structural systems engineering drives megatall buildings' ability to withstand gravity loads of immense magnitude alongside lateral forces from wind, seismic events, and occupant movements. Core and outrigger structural schemes govern modern megatower stability. The buttressed core system, exemplified by Dubai's Burj Khalifa, merges a central hexagonal reinforced concrete core with radiating wings interconnected by outriggers and belt trusses, distributing bending moments and torsional forces efficiently, reducing material usage while enhancing stiffness. Wind tunnel testing and computational fluid dynamics. CFD simulations identify and mitigate vortex shedding and pressure differentials, minimizing occupant discomfort and structural fatigue. Alternative megastructural concepts include tube-in-tube systems and mega-column grids, leveraging ultra-high-strength concrete and steel composites, ensuring slenderness and floor plate flexibility. Base isolation techniques, and supplemental damping systems such as tuned mass dampers and viscous fluid dashpots offset dynamic excitations. These systems require precise nonlinear finite element modeling, addressing time-dependent material behavior, cracking, creep, and shrinkage expansions, evaluating performance over decades under changing climate and load patterns. Materials innovations form a bedrock enabling vertical scale and performance. Development of ultra-high performance concrete UHPC, marrying high strength, ductility, and durability permits slender columns and longer spans, reducing foundation work and enhancing usable space. High-strength steel alloys with optimized toughness resist tension and shear while maintaining weldability critical for prefabricated modules. Fiber-reinforced polymer FRP composites supplement corrosion protection and fatigue resistance in structural and facade elements. Fire-resistant materials and coatings satisfy increasingly stringent safety standards, essential for occupant protection and insurance requirements. Vertical transportation engineering addresses occupant mobility challenges, rising exponentially with height and density. Elevator systems incorporate multi-deck cars, double or triple deck arrangements, and express shuttle elevators partitioning lobbies and sky lobbies to optimize flow. Regenerative drives harvest energy during braking cycles, reducing overall consumption. Advanced control algorithms employing AI optimize elevator dispatch, reducing wait times and power demand. Destination control systems cluster passengers with shared destinations, minimizing stops and improving throughput. Emergency evacuation elevators, designed with pressurization and fire defense compartments, promote rapid, safe evacuation avoiding stairwells. Mechanical, electrical, and plumbing systems integrate intelligent building management systems, monitoring and controlling HVAC, lighting, water, and energy systems dynamically adjusting to occupancy, external weather, and demand fluctuations. Innovations such as chilled beams, heat recovery ventilation, and radiant cooling systems increase energy efficiency and occupant comfort. Water supply systems implement gray water recycling, rainwater harvesting, and water-saving fixtures supporting sustainability. Facade engineering couples aesthetics and performance balancing, daylighting, solar heat gain reduction, natural ventilation potential, and acoustic insulation. Double-skin facades with operable components facilitate adaptive responses to climatic variables, enhancing thermal comfort and reducing HVAC loads. High-performance glazing incorporates spectrally selective coatings and photovoltaic integration, enabling net zero or positive energy facades. Construction methodologies embrace modular prefabrication, enabling tight tolerance production, quality assurance, and rapid assembly, reducing on-site labor, waste, and risk exposure. Climbing formwork, automated rebar and concrete placement, and robotic facade installation systems elevate efficiency within constrained urban sites. Just-in-time logistics synchronize component deliveries with erection activities, minimizing storage and traffic disruptions. Operational complexity involves advanced sensor networks underpinning digital twins monitoring structural integrity, energy consumption, air quality, and occupant behavior, enabling predictive maintenance, fault detection, and user-centered building controls. Data analytics support optimization of cleaning schedules, elevator grouping, and space utilization, promoting sustainability and occupant satisfaction. Resilience planning integrates redundancy in critical systems, including power supply with multiple feeds and battery backups, water storage and filtration, and fire suppression systems employing water mist and compartmentalization. Seismic mitigation designs protect against rare but catastrophic events, preserving life safety and asset longevity. Environmental certifications including LEED Platinum, Well Building Standard, and BREEAM Communities Guide Holistic Sustainability, encompassing health, wellness, energy efficiency, and social responsibility, ensuring buildings contribute positively to urban ecosystems and community well-being. Socio-cultural dimensions feature inclusive design principles, ensuring accessibility for differently abled individuals and provision of public spaces, promoting social interaction and cultural programming within vertical communities. Finance and governance. Recognize mega high-rise projects as long-term investments necessitating comprehensive risk management, including insurance for delays, material price escalations, and operational disruptions. Collaborative stakeholder governance involving developers, contractors, municipal authorities, and tenant representation ensures aligned incentives and transparency. Globally iconic towers serve as hubs of commerce, residence, hospitality, and culture, embedding megaprojects within urban narratives while driving technological advancement, reinforcing regional identities and economies. These vertical megaprojects push the boundaries of engineering science, blending structural mechanics, materials innovation, systems integration, and human-centered design into soaring monuments of progress, exemplifying complexity mastered through vision and precision. Complex transportation megaprojects constitute the lifeblood of global mobility, knitting vast territories and urban centers through intricate, technology-rich networks that transcend mere infrastructure to become catalysts of economic growth, social integration, and environmental sustainability. These undertakings embody immense technical, logistical, and governance complexities, merging multimodal integration, cutting-edge technological systems, and sprawling service ecosystems across fluctuating terrain, regulatory landscapes, and stakeholder expectations. High-speed rail systems exemplify transformative complexity in connecting metropolises at 300 plus kilometers h velocities, demanding exacting standards in route alignment, track design, rolling stock integration, signaling, and urban interface. China's high-speed rail network surpassing 40,000 kilometers showcases exponential scalability, integrating dedicated track with conventional rail, creating hybrid mobility corridors supporting passenger and freight flows. Challenges include precise geotechnical characterization, addressing soil liquefaction, tunnel stability under soft ground, and seismic resilience engineered through base isolators, energy dissipation devices, and flexible viaduct design. Alignment tolerances within millimeter scale require continuous welded rails laid on vibration isolating concrete slabs to maintain dynamic stability and passenger comfort. Aerodynamic rolling stock designs reduce drag and noise emissions, employing computational fluid dynamics shaping and lightweight construction through aluminum alloys and composites. Signaling systems represent a crowning integrant of safety and efficiency, integrating communications-based train control, CBTC, with positive train control, PTC, architectures enabling automated train separation, speed regulation, and real-time system redundancy. Integration with legacy networks demands comprehensive interface design, testing, and commissioning protocols, ensuring uninterrupted interoperability. Operational command centers incorporate AI algorithms, predicting maintenance needs, schedule adjustments, and incident mitigation, dynamically optimizing network throughput under varied demand scenarios. Mega airports such as Istanbul Airport or Beijing Daoping integrate multimodal transportation connectors, including high-speed rail, metro, and roadway networks within colossal terminal complexes. Engineering encompasses multi-layered apron and taxiway designs optimized through pavement load modeling and drainage systems, engineered for peak rainfall intensities and temperature fluctuations. Check-in and security systems incorporate biometric and AI technologies efficiently processing millions of passengers annually while preserving security integrity. Baggage handling employs automated sorting, conveyance, and tracking systems utilizing RFID sensors integrated with centralized monitoring platforms, minimizing loss rates and turnaround times. Urban transport mega initiatives like London's Crossrail and the New York 2nd Avenue subway navigate dense, historically layered environments, requiring sophisticated tunneling methods paired with advanced microtunneling and shield technologies, minimizing surface settlement and structural interference. Construction sequencing adapts to constraints imposed by active urban life through nighttime work windows, vibration suppression techniques, and noise barriers balancing progression speed with community coexistence. Real-time monitoring through surface deformation measurement networks enables preventive response to excavation-induced ground movements, protecting heritage and utilities. Electric and autonomous vehicle integration within transport megaprojects embrace vehicle-to-everything V2X communication standards, charging infrastructures, and smart grid interaction, enabling intelligent route optimization, congestion mitigation, and emission reduction. Comprehensive data analytics platforms aggregate traffic flows, modal shift patterns, and environmental impacts, supporting adaptive policy implementation aligned with sustainable urban mobility plans. Logistical complexity surpasses physical construction involving global supplier networks, materials logistics, equipment deployment, and workforce mobilization, harmonized through AI-supported scheduling, digital twin models for scenario testing, and blockchain-secured procurement transactions, enhancing transparency and reducing fraud. Financial architectures blend governmental investment, private finance initiatives, and international development funding, structured through public-private partnerships, embodying risk-sharing, performance-based compensation, and long-term operational oversight. Stakeholder engagement integrates multi-level governance, including municipalities, regulatory agencies, community groups, and private sectors, fostering alignment through transparent communication, dispute resolution frameworks, and shared value realization. Environmental management prioritizes ecological connectivity preservation, air quality improvement, and noise attenuation, employing green infrastructure design supporting biodiversity and urban livability. Security considerations address cyber-physical system vulnerabilities intrinsic to increasingly digitalized transport networks, deploying layered cybersecurity protocols, intrusion detection, and resilient system architectures. Education and workforce training programs evolve, focusing on multidisciplinary integration encompassing railway engineering, data science, urban planning, and environmental stewardship, equipping professionals for megaproject complexity. Together, these transportation megaprojects exemplify holistic engineering systems navigating unprecedented complexity in pursuit of connective infrastructure that propels economies, communities, and sustainable futures. Complex energy megaprojects lie at the crossroad of extreme engineering challenge, social necessity, and ecological stewardship. These monumental ventures stretch from harnessing the power of water through sprawling hydroelectric installations, securing reliable baseload generation with nuclear complexes, to pioneering vast renewable energy arrays capturing wind, sun, and emerging bioenergy sources. The intricacies intertwined within these projects demand extraordinary multi-domain expertise, adaptive management, and persistent innovation. Hydroelectric megaprojects such as China's Three Gorges Dam epitomize the scale and multifaceted complexity of harnessing riverine power, occupying an expanse over 2 kilometers wide. The dam combines flood control, navigation enhancement, and electric power generation, with a staggeringly high installed capacity exceeding 22,000 megawatts. Engineering challenges include managing hydrological variability in an immense drainage basin, geological stabilization of caverns housing turbines, and sedimentation management vital for reservoir sustainability. The integration of multiple turbine generators requires precision hydraulic engineering optimizing flow distribution under variable demand while safeguarding against cavitation and vibration-induced fatigue. Construction logistics span diversion channel excavation, concrete placement measured in millions of cubic meters, utilizing thermally controlled pouring regimes, mitigating cracking, and enormous-scale relocation programs affecting over 1 million inhabitants. Ecosystem impacts demand continuous monitoring, plus development of fish passage systems and sediment flushing to preserve aquatic ecology. Sophisticated control systems balance hydraulic, mechanical, and electrical synchronization, ensuring grid stability amid fluctuating water inflows. Nuclear energy megaprojects deliver high-density, reliable power but invoke unparalleled safety, design, and regulatory complexities. The Kashiwazaki Kariwa nuclear power plant, among the world's largest, incorporates multiple boiling water reactors, engineered to endure intense seismic activity characteristic of Japan. Structural designs emphasize catastrophic resilience through multi-redundant containment vessels, seismic isolation foundations, and emergency core cooling systems with active and passive redundancies. Reactor core thermal hydraulics must maintain stable neutron flux distributions, preventing localized overheating, while fuel assembly design optimizes neutron economy and burnup. Engineering extends to spent fuel management facilities, incorporating dry cask storage and precise radiation shielding. Regulatory compliance involves continuous safety assessments, probabilistic risk analysis, and rigorous operational oversight, integrating plant-wide monitoring systems, capturing a spectrum of safety parameters. Public involvement and transparent communication remain critical, reflecting heightened societal scrutiny. Renewable energy megaprojects encompass sprawling wind farms, expansive solar parks, and bioenergy complexes often situated in remote or environmentally sensitive regions. The Gansu wind farm in China spans thousands of turbines strategically spaced to mitigate wake losses, incorporating advanced aerodynamic blade design enabled by composite materials. Foundation engineering confronts challenges ranging from permafrost soils to desert sands, requiring site-specific geotechnical interventions, ensuring structural stability. Smart supervisory control and data acquisition SCADA systems interlink turbines, coordinating output smoothing, facilitating grid integration. Solar megaprojects utilize multi-junction photovoltaic cells and dual-axis trackers, maximizing insolation capture, whose layouts necessitate terrain-adapted geospatial optimization, minimizing shading and land use conflict. Environmental monitoring addresses avian and soil impacts utilizing mitigation technologies, including radar monitoring and habitat preservation zones. Energy storage megaprojects increasingly integrate to mitigate intermittent generation's inherent variability. Pumped hydro storage facilities, large lithium-ion battery clusters, and innovative hydrogen production plants combine electrochemical, mechanical, and control engineering, delivering flexible load balancing, frequency regulation, and emergency backup. Scale brings challenges in thermal management, lifespan optimization, and grid synchronization. Advanced material science underpins battery longevity, safety enhancements, and energy density improvements, critical for these large-scale deployments. Transmission megaprojects underpin energy transfer over vast distances employing ultra-high voltage alternating current UFAC or direct current HVDC lines designed with novel low-resistance conductors, optimized tower structures accommodating mechanical and environmental loads, and sophisticated substation automation ensuring resilience and fault-rapid isolation. Environmental and social governance permeate all phases. Impact assessments guide species preservation, water resource management, community resettlement, and equitable benefit sharing. Adaptive environmental management follows through strict compliance monitoring and collaborative stakeholder engagement, ensuring long-term ecosystem health and societal support. Financial engineering solutions mobilize concatenated capital pools, blending public investment, private equity, development finance, and green financing instruments, aligning stakeholder incentives around sustainability and risk mitigation. Integration of digital technologies including digital twins, real-time sensor networks, and AI-supported predictive maintenance enhance operational efficiency, asset longevity, and environmental compliance. Complex energy megaprojects embody the nexus of engineering prowess, societal progress, and planetary stewardship, constructing critical infrastructure powering future generations with resilience, responsibility, and innovation. Water resource management megaprojects tackle some of the most profound challenges affecting humanity's survival and prosperity, securing reliable supply, enabling agriculture at scale, and protecting populations and habitats against increasingly capricious hydrological extremes. These vast systems embody unparalleled technical, environmental, and social intricacies, requiring harmonious integration of civil infrastructure, ecological stewardship, community engagement, and adaptive management. Reservoir megaprojects like India's Sardar Sarovar Dam on the Narmada River epitomize complexity at the confluence of engineering scale and multifaceted societal impact. The dam's arch-gravity design spans nearly 1.2 kilometers, creating a reservoir extending over 375 square kilometers. Engineers confronted challenging geological conditions with varying rock qualities, mandating varied foundation treatments and concrete mix designs, ensuring structural stability and minimizing seepage through contact zones. Spillway capacity designs balance flood routing efficiency with downstream ecosystem preservation, guided by hydrodynamic modeling incorporating climate change projections, addressing monsoon variability and extreme event occurrence. The vast reservoir serves multiple purposes: hydroelectric generation, irrigation supply, drinking water provisions and flood mitigation, demanding integrated operational rules, balancing competing demands across seasonal cycles. Sedimentation management remains a persistent challenge tackled via watershed afforestation, sediment sluicing, and sediment basin construction, constraining reservoir lifespan degradation. The megaproject entailed resettling hundreds of thousands, necessitating transparent compensation, livelihood rehabilitation programs, and social audit processes addressing cultural heritage preservation and gender equity. Irrigation complexities unfold vividly in the Indira Gandhi Canal system, one of the world's longest irrigation channels transporting Himalayan water into the arid Thar Desert. Canal engineering optimized gradient profiles, ensuring uniform water velocities, minimizing leakage and siltation, employing cutting-edge lining technologies such as geomembranes and concrete linings adapted for thermal expansion and local soil interactions. The system implements automated control structures, integrating remote sensing and SCADA systems, managing flow rates and demand responsiveness, enhancing water use efficiency, and minimizing wastage. The immense scale and geographic reach require comprehensive geospatial information systems, GIS, managing network conditions, alerting for blockage risks, and coordinating maintenance operations. Environmental stewardship demands integrated salinity control measures, combating soil degradation, complemented by sustainable groundwater recharge management, preserving aquifer health. Socioeconomic programs foster community participation in water governance, supporting equitable distribution and conflict resolution, enhancing system resilience. Flood management megaprojects embody combinations of hard and soft engineering responses. The Netherlands' Room for the River program exemplifies a paradigm shift favoring natural floodplain restoration alongside dikes and storm surge barriers. Projects strategically relocate dikes inland, creating controlled flooding areas, reestablishing wetlands, improving groundwater replenishment, and enhancing biodiversity. Hydraulic modeling integrating large-scale river basin inputs forecasts flood dynamics, informing multi-objective designs, balancing flood protection with environmental restoration and recreational opportunities. Moving beyond traditional defense, infrastructures incorporate adaptive elements, movable storm surge barriers like the Oosterschelde barrier, deploy massive gates during storm events while maintaining tidal flow, supporting estuarine ecosystems. Extensive monitoring networks use satellite observation, acoustic Doppler current profilers, and water level sensors, feeding centralized control centers, enabling real-time flood forecasting and emergency management. In arid and semi-arid regions, desalination megaprojects such as Spain's Almeria plant couple seawater reverse osmosis with cogeneration power plants, optimizing energy usage critical. Given desalination's typically high carbon footprint, engineering solutions emphasize corrosion-resistant materials, efficient brine management, minimizing environmental impacts, and modular plant designs facilitating scalable deployment. Integration with renewable energy sources, solar, thermal, and photovoltaic, pushes advancements toward carbon-neutral water supply. Urban water supply megaprojects integrate smart systems, deploying sensor networks, measuring pressure, flow, and leakages, allowing real-time adjustments reducing losses, which in some systems exceed 30%. Advanced metering infrastructure, AMI provides customer usage feedback, promoting conservation. Modular wastewater recycling plants, employing membrane bioreactors, and constructed wetlands, close urban water loops, contributing to sustainability and resilience. Digital transformation permeates water management through digital twin technologies, simulating entire hydrological and infrastructural networks, incorporating stochastic climate projections, supporting adaptive optimization in allocation and maintenance planning. Machine learning algorithms predict demand patterns, water quality fluctuations, and system failures, enhancing preemptive interventions, reducing outages and consumption spikes. Societal complexities inherent in water megaprojects necessitate multi-stakeholder governance frameworks, incorporating indigenous knowledge, community voices, and equitable benefit sharing, incorporating gender, socio-economic equity, and rights frameworks, ensuring water access is a universal human right respected beyond infrastructure design. Environmental impact assessments incorporate cumulative and transboundary analyses, ensuring holistic watershed health considering fauna migrating through connected aquatic and riparian habitats. Climate change amplifies uncertainties, mandating flexible designs capable of operating under wider hydrological demand ranges, including prolonged droughts and flooding, requiring integrated water-energy-food nexus approaches. Embedding megaprojects within resilient regional systems. Economic mechanisms. Supporting sustainable water megaprojects include blended finance sourcing, public, private, and multilateral funds, tied to performance and social impact indicators fostering innovation, diffusion, and inclusiveness. In essence, water resource megaprojects synthesize monumental civil infrastructure with complex ecological systems and social fabrics, constituting engineered lifelines, sustaining human civilization amid evolving environmental and demographic pressures. Urban infrastructure megaprojects form the foundational skeletal framework, upon which the vitality and resilience of burgeoning metropolises depend, intertwining physical connectivity, technological innovation, and sustainable resource management within complex social and environmental matrices. These projects encompass sprawling ports serving as global trade gateways, cutting-edge logistics hubs, optimizing supply chains, and emergent smart city ecosystems, embedding pervasive digital intelligence into every facet of urban experience. Their realization demands an extraordinary fusion of multidisciplinary engineering, visionary planning, and adaptive governance, capable of navigating the complexities inherent in modern urban dynamics. Megaports represent critical nodes in the intricate global supply chain, facilitating the large-scale movement of goods, raw materials, and energy resources, essential for worldwide economic continuity. The Port of Shanghai exemplifies capacity and complexity, sprawling over thousands of hectares along the Yangtze estuary and handling tens of millions of TEUs annually. Engineering these massive complexes involves creating deep water berths dredged beyond 15 meters to accommodate ultra-large container vessels, with quay walls designed to absorb dynamic forces from berthing maneuvers often exceeding hundreds of kilonewtons. Crane gantries, each supported by steel structures optimized for both load resistance and rapid container handling efficiency, traverse precisely laid concrete and gravel yard surfaces, choreographed for uninterrupted cargo flow. State-of-the-art terminal operating systems integrate RFID tracking, GPS positioning, and real-time analytics ensuring seamless coordination among maritime, rail, and road modalities. Environmental stewardship entails sediment and turbidity control during dredging, strict ballast water management compliant with international maritime conventions, and hybrid or fully electric cranes reducing emissions and local air pollution. Logistics megahubs underpinning just-in-time delivery and supply chain resilience function, as orchestrated symphonies of warehousing, transportation, customs processing, and distribution. Facilities such as Dubai Logistics City strategically interface air, sea, and land transportation, leveraging swathes of warehousing equipped with automated high bay racking systems and AI-directed robotic order pickers, empowered by vision systems and machine learning analytics. Building layouts optimize cross-docking operations to minimize product dwell time, utilizing simulation-driven spatial planning that dynamically adapts storage density against handling speed requirements. Energy reliability is assured via on-site photovoltaic arrays, coupled with battery storage and smart microgrids, enabling resilience against grid disturbances. Advanced building automation systems regulate climate control, lighting, and security while maximizing operational efficiency and reducing carbon footprint. Emergent smart city megaprojects exemplify urban evolution, embedding sensor networks, IoT devices, and cloud-based platforms creating real-time data integration and analytics, transforming infrastructure, services, and governance. Urban operation centers harness machine learning and big data to optimize traffic flow via adaptive traffic lights, anticipate power grid demand peaks, regulating distributed energy resources, and improve waste management through optimized collection routes coordinated by sensor-equipped bin networks. Communication backbones leveraging 5G and fiber optics enable autonomous vehicle operation, remote healthcare delivery, digital public service platforms, and participatory citizen engagement apps, fostering transparency and collaborative decision-making. Water systems embed smart metering, pressure management modules, and leak detection technology, effectively minimizing losses and ensuring equitable supply in often stressed urban water networks. Wastewater treatment innovations leverage decentralized modular facilities, applying membrane bioreactor technologies, reducing energy usage and footprint. Urban energy ecosystems empower distributed renewable generation, demand response programs, and integrated electric vehicle charging networks, balancing grid demand and optimizing resource use. Urban logistics and transportation integrate multimodal hubs, uniting rail, metro, bus rapid transit, and cycling infrastructure, maximizing last-mile connectivity and reducing urban congestion and emissions. Station design employs biometrics, AI-driven crowd flow modeling, and universal accessibility features, integrating form and function, supporting high passenger throughput and safety. Cybersecurity emerges as a paramount concern within this hyper-connected urban fabric. Multi-tiered encryption, intrusion detection systems, and resilient network architectures safeguard critical infrastructure and citizen data against cyber threats, preserving trust and continuity. Privacy frameworks guide data governance, ensuring responsible sensor data collection. Cultural competence and inclusivity permeate smart city design and implementation. Multilingual interfaces, culturally adapted communication campaigns, and targeted outreach ensure technology inclusiveness, addressing disparities to prevent digital divides exacerbating social inequity. These urban megaprojects demand coordination across heterogeneous stakeholder groups, government agencies, private entities, civil society, and residents, managed through collaborative governance platforms, ensuring transparency, accountability, and adaptability to evolving urban dynamics. Sustainability certifications such as LEED ND and Well Communities benchmark urban developments, promoting health, equity, and environmental performance, validating megaproject impact beyond traditional engineering metrics. Innovations in digital twin models replicate entire urban ecosystems, encompassing transport, energy, water, and social infrastructure, enabling scenario analysis, predictive maintenance, and participatory planning, empowering informed governance and community engagement. Construction logistics confront dense urban constraints necessitating modular, prefabricated building systems, just-in-time material delivery, and real-time coordination minimizing disruption and accelerating timelines. Financing architectures blend municipal bonds, public-private partnerships, international loans, and impact investments, providing diverse capital flows, balancing risk and return, aligned with sustainable urban development goals. Phase-wise implementation strategies adapt to urban growth trends and economic cycles, ensuring scalable, flexible infrastructure deployment aligned with long-term visionary urban plans. Ultimately, urban infrastructure megaprojects signify holistic engineering endeavors sensitively balancing complexity, scale, technological advancement, and societal well-being. They embody humanity's capacity to orchestrate and integrate massive, interconnected systems, not only sustaining but enhancing quality of life in an era of rapid urban transformation. Aerospace and space exploration megaprojects inhabit an extraordinary realm where cutting-edge technology, unyielding precision, and boundless human ambition forge new pathways beyond Earth's atmosphere. These projects encompass vast and intricate launch facilities, orbital platforms serving as scientific and habitation hubs, and ambitious interplanetary missions pushing humanity's frontier into the solar system and beyond. Their monumental complexity emerges not only from extreme engineering challenges, but also from the intertwining of international collaboration, long-term sustainability, and high-stakes risk management in unforgiving environments. At the foundation of aerospace megaprojects lie launch complexes, gigantic facilities accommodating towering rockets, immense fueling systems, and sophisticated ground support infrastructure. The Kennedy Space Center's Launch Complex 39 embodies engineering marvels, managing the assembly, fueling, and launch of vehicles weighing thousands of tons. These complexes integrate massive vehicle assembly buildings, VABs, enabling vertical assembly with extreme precision, crawler transporters designed to carry hundreds of tons over uneven terrain at walking speeds, flame trenches engineered to deflect millions of liters per second of rocket exhaust, protecting critical infrastructure, and specialized fueling systems providing cryogenic propellants, stored at temperatures reaching minus 253 Celsius. Ground support equipment encompasses intricate power distribution networks, housing uninterrupted power supplies, safeguarding sensitive electronics, while environmental control facilities maintain temperature and humidity within narrow margins, vital for vehicle and personnel health. Rocket propulsion systems themselves represent unfathomable engineering achievements. Liquid-fueled engines blend turbopumps capable of delivering propellants at hundreds of bars pressure, with combustion chambers engineered to withstand extreme thermal loads and vibration. Solid rocket boosters provide high-thrust appendages requiring tailored grain designs to regulate burn rates and ensure structural integrity under extreme dynamic loading. Reusable launch vehicle stages integrate aerodynamic control surfaces, grid fins, and advanced thermal protection systems, enabling controlled hypersonic re-entry and soft landings vital to reducing operational costs and increasing flight cadence. Propellant management systems harness advanced fluid dynamics, ensuring stable delivery across varying acceleration regimes and gravitational fields. Orbital platforms, epitomized by the International Space Station (ISS), function as microgravity laboratories, habitats, and communication nodes. Their modular construction requires precise alignment and integration of multinational components fabricated worldwide. Structural engineering must ensure resistance to micrometeoroid impacts and space debris through multi-layered shielding, combining aluminum alloys and advanced polymer materials. Radiation shielding, employing polyethylene and water layers, mitigates cosmic ray exposure, safeguarding crew health over extended missions. Life support systems recycle water and air through complex chemical and physical processes, incorporating electrolysis, carbon dioxide scrubbing, humidity control, and microbial ecosystems maintaining atmospheric stability. Power generation from expansive photovoltaic arrays is regulated via maximum power point tracking and redundancy to ensure uninterrupted supply to mission-critical systems. Robotic manipulators such as Canadarm2 extend maintenance capabilities, enabling remote payload handling, inspection, and interfacing with visiting spacecraft. Interplanetary missions stretch the envelope further, confronting delayed control times, harsh environments, and complex entry, descent, and landing (EDL) scenarios. Mars rover missions like Perseverance navigate unpredictable terrain, employing autonomous hazard detection and safe path planning embedded within onboard computer architectures. Planetary protection protocols integrate sterilization and containment systems, preventing cross-contamination, preserving extraterrestrial ecosystems. Propulsion hybridization explores solar-electric propulsion merging ion drives with chemical engines, enabling high delta-V maneuvering for deep space exploration. Data transmission systems battling immense distances employ advanced error correction algorithms, adaptive coding, and high-gain antennas, ensuring anomaly-free communication across millions of kilometers. Powering these vehicles integrates radioisotope thermoelectric generators, RTGs, and solar arrays tailored for minimal solar flux. Ground support networks coordinate orbital and interplanetary operations via globally distributed antenna arrays within the Deep Space Network (DSN), providing telemetry, tracking, and command management. Data centers analyze a torrent of sensor readings and scientific outputs, employing AI-enabled anomaly detection and decision support to maintain mission integrity. Software engineering across aerospace megaprojects demands real-time deterministic control systems with fail-safe watchdog timers, redundant processor architectures, and high-integrity coding standards, often adhering to DO-178C Level A certification, assuring maximal reliability. Simulation environments replicate physical dynamics and environmental conditions, guiding design validation, crew training, and contingency planning. Safety engineering pursues rigorous certification spanning human rating requirements, including launch escape systems, launch vehicle and ground support system redundancy, comprehensive hazard analyses, and operational fail-safe designs underpinning crewed missions. Emergency preparedness incorporates detailed evacuation protocols, underpinned by frequent, realistic drills and robust communication pathways. The global nature of aerospace megaprojects fosters international cooperation involving shared funding, technology transfer, and joint mission planning, exemplified by partnerships within the ISS consortium or multinational planetary exploration programs, aligning resources toward common scientific objectives. Sustainability considerations lead efforts to minimize orbital debris through end-of-life deorbiting strategies, material recycling research, and mission design focused on planetary protection and resource efficiency. Financially, aerospace megaprojects marshal multinational government allocations, combined with private sector innovation, balanced through phased development stages, and risk-sharing contracts managing the interplay of technological uncertainty and commercial viability. This domain represents human civilization's highest convergence of technological innovation, scientific inquiry, and visionary aspiration, transforming engineering complexity into the tangible exploration and utilization of space. Digital technologies and automation represent a seismic paradigm shift, catalyzing transformative progress in the design, construction, operation, and maintenance of megaprojects. These technological pillars integrate advanced computation, connectivity, sensing, and robotics, orchestrating intricate systems with speed, precision, adaptability, and intelligence that far exceed traditional engineering methods. Their pervasive incorporation redefines how complexity is managed, risks are mitigated, quality is controlled, and value is delivered throughout the megaproject lifecycle. Building Information Modeling (BIM) serves as a digital cornerstone by creating comprehensive multidimensional virtual representations of physical assets linked to rich semantic data. Beyond three-dimensional geometry, BIM encapsulates time sequencing 4D, cost estimation 5D, sustainability analytics, and lifecycle management tools, enabling integrated project delivery paradigms. These models allow multidisciplinary stakeholders, architects, engineers, contractors, owners, to concurrently collaborate on a single platform, minimizing conflicts through automatic clash detection, coordinated alterations, and optimized constructability analyses. Parametric and generative design techniques embedded within BIM environments enable exploration of vast design solution spaces guided by performance criteria, simulation outputs, and stakeholder priorities, driving innovation while harmonizing constraints. Digital twin technology extends BIM from design and construction into real-time operation and maintenance, constructing live, intelligent virtual models, continuously fed by sensor data streams from embedded Internet of Things IoT devices. These digital twins simulate structural behavior, environmental conditions, and system interactions, enabling predictive maintenance, anomaly detection, operational optimization, and scenario planning. For example, bridges instrumented with strain gauges, accelerometers, and environmental sensors monitor dynamic load effects and deterioration rates, providing engineers actionable insights that prevent failures and optimize maintenance scheduling, reducing costs and downtime significantly. Urban infrastructure digital twins amalgamate multiple subsystems, transport, energy, water, waste, into unified platforms, enabling holistic city management with responsiveness unparalleled in traditional monitoring. Artificial intelligence (AI) and machine learning (ML) algorithms analyze vast datasets generated throughout megaproject workflows, uncovering latent patterns, anticipating risks, optimizing resource allocation, and enabling automated decision-making. AI-enhanced generative design iteratively evolves structural configurations, maximizing strength-to-weight ratios, cost efficiency, and environmental performance by embracing multi-dimensional optimization beyond human cognitive limits. Predictive maintenance models ingest sensor arrays, historic records, weather information, and operational logs to forecast component failures, enabling preemptive repairs, optimizing asset availability. In construction management, AI models predict productivity bottlenecks, worker fatigue risks, and supply chain disruptions, facilitating dynamic mitigation strategies. Natural language processing NLP automates contract analysis and regulatory compliance checks, accelerating administrative workflows and reducing errors. Cloud computing infrastructure provides elastic computational capacity and collaborative environments, enabling geographically distributed multidisciplinary teams to simultaneously access, modify, and update complex project data. Cloud platforms ensure data redundancy, cybersecurity, and version control, critical for maintaining project integrity and continuity over megaprojects spanning years or decades. Parallel high-performance computing enables detailed multi-physics simulations integral in earthquake, wind, and thermal performance modeling, supporting robust, reliable designs. Automation technologies permeate physical construction workflows with robotics and unmanned systems undertaking repetitive, hazardous, or precision-demanding tasks. Automated guided vehicles (AGVs) transport heavy loads across construction yards, minimizing labor risk and increasing throughput. Robotic bricklaying, 3D concrete printing, and modular prefabrication systems accelerate construction tempo while enhancing quality control through automated inspection and tolerance management. Aerial and terrestrial drones equipped with high-resolution cameras, LiDAR, and thermal imaging perform rapid site surveying, progress monitoring, and safety inspections in environments traditionally difficult or dangerous for human access, feeding AI analysis pipelines, enhancing situational awareness and planning. Digital workflows integrate Internet of Things IoT sensor networks, measuring environmental parameters, including air quality, noise levels, temperature, dust, supporting health and safety, compliance, and environmental sustainability. Wearable devices track worker vital signs and exposure metrics, enabling personalized health monitoring and early incident detection, augmenting traditional safety protocols. Cybersecurity frameworks have become paramount as digital interconnectivity expands attack surfaces, threatening intellectual property, operational continuity, and safety-critical systems. Defense architectures employ multi-layered encryption, access control, intrusion detection, and anomaly recognition combined with comprehensive risk assessments and incident response plans, ensuring the resilience of integrated digital ecosystems. Data governance policies ensure ethical data stewardship, respecting privacy, accuracy, transparency, and regulatory compliance. Open data initiatives foster innovation ecosystems, enabling knowledge dissemination while safeguarding proprietary and sensitive information. Augmented reality, AR, and virtual reality VR technologies revolutionize training, design communication, and remote collaboration by immersing stakeholders within realistic, interactive digital twins, fostering enhanced understanding, error reduction, and stakeholder engagement, bridging spatial and temporal divides. Despite profound automation advances, human expertise remains indispensable, with digital augmentation enhancing judgment, creativity, and ethical reasoning embedding responsibility and adaptability at megaproject cores. The digital transformation of megaproject engineering propels the field into an era marked by agility, precision, resilience, and integration. It enables humanity not only to conceive and construct vast infrastructure, but to operate and maintain living systems, optimized continuously, anticipating and adapting to evolving demands and challenges. This technological renaissance marks an inflection point, where complexity becomes manageable through intelligent connected networks, advancing mega-project performance, while safeguarding quality, safety, and sustainability in unprecedented fashion. Materials innovation underpins the creation and longevity of megaprojects, serving as the essential substrate upon which the monumental scale, resilience, and sustainability of infrastructure rely. This domain sits at the confluence of advanced chemistry, physics, nanotechnology, and applied engineering, producing materials not merely characterized by strength or durability, but engineered for multifunctionality, adaptability, and environmental responsibility. Such advances redefine possibilities in mega project execution and performance, presenting novel opportunities and formidable challenges across design, fabrication, construction, and maintenance. Concrete remains the most ubiquitous structural material worldwide, and its evolution continues as a critical driver of megaproject advancement. Ultra-high performance concrete UHPC, integrating optimized particle packing, silica fume, superplasticizers, and microfibers, achieves compressive strengths exceeding 150 MPa, alongside exceptional durability and ductility. Its dense, low permeability matrix confers superior resistance to freeze-thaw cycles, chloride ion penetration, and sulfate attack key for marine and harsh environments faced by mega bridges, dams, and tunnels. Nanoparticles such as nanosilica enhance hydration kinetics, reduce porosity, and impart self-healing via autogenous crack sealing. Green concrete formulations reduce carbon intensity by substituting clinker with industrial waste supplementary cementitious materials, SCMs like fly ash, slag, and calcined clays, significantly reducing CO2 emission footprints. Incorporation of calcium carbonate deposition bacteria within concrete matrices actively repairs microcracks, extending service life. Steel technologies have similarly leapt forward with developments in high-strength, low-alloy HSLA steels, weathering steels, and stainless alloy variants tailored for specific exposures. HSLA steels balance tensile strength with improved weldability and toughness, enabling slimmer profiles, reducing overall structural weight and foundation loads. Weathering steel forms protective oxide layers, reducing corrosion in exposed structures, extending maintenance intervals essential for megabridges or offshore platforms. Metallurgical innovations produce ultra-fine grain steels, enhancing fatigue performance, guarding against crack initiation under cyclic loads prevalent in long-span bridges and high-rise buildings. Advanced coatings and cathodic protection systems further augment steel longevity, employing durable, environmentally compatible compounds resisting marine, industrial, and UV exposures. Fiber-reinforced polymer FRP composites constitute a revolutionary class of materials transforming both new construction and retrofitting approaches. Carbon fiber reinforced polymers CFRPs provide exceptional strength-to-weight ratios and corrosion resistance. Instrumental in reinforcing aging infrastructure, unable to support increased contemporary loads. Applications span pre-stressed bridge girders, seismic strengthening of columns, and lightweight cladding panels. Glass and basalt fiber composites offer cost-effective alternatives suited for non-structural applications. Challenges include ensuring long-term bond durability with concrete and fire resistance. Research advances such as hybrid composite laminates and fire-resistant resins address these limitations. Prefabricated FRP components enable modular construction, enhancing precision and reducing assembly durations. Innovations in smart materials embed sensing, self-healing, and adaptive functionalities within construction materials. Piezoelectric and fiber optic sensors integrated in concrete or composites monitor strain, temperature, humidity, and crack propagation, transmitting real-time health data, enabling proactive maintenance and life cycle extension. Shape memory alloys incorporated within seismic dampers and bridge bearings enable reversible deformation, absorbing vibrational energy and facilitating post-event structural recovery, minimizing repair demands. Self-healing polymers and hydrogels contain micro-encapsulated healing agents released upon damage, triggering polymerization, sealing cracks autonomously, prolonging durability under stress and environmental attack. Advanced metals such as titanium alloys and aluminum-lithium composites find applications in aerospace megaproject components and high-rise architectural elements, where strength, low weight, and corrosion resistance are critical, despite cost challenges. Research into superalloys for turbine blades and critical machinery enhances thermal stability and fatigue life, integral for power generation megaproject efficiency. The advent of additive manufacturing, 3D printing for large structural components represents a paradigm shift, enabling fabrication of bespoke, optimized geometries with complex internal structures unachievable through traditional casting or machining. This technology reduces material waste, labor costs, and accelerates production cycles, while enabling rapid prototyping and on-site manufacturing, vital for remote or logistically challenging megaproject sites. Materials for additive manufacturing advance to include high-strength concrete mixes, steel alloys, polymers, and ceramic matrices, customized for mechanical performance and durability. Fire-resistant materials and coatings incorporate intumescent layers, ceramic composites, and mineral additives protecting critical load-bearing components, essential in high-rise and tunnel megaprojects to preserve structural integrity and occupant life under extreme fire conditions. Regulatory evolutions demand continuous material performance verification, pushing innovation toward non-toxic, sustainable fire protection systems. Nanomaterials research leads to revolutionary prospects. Graphene-enhanced concretes and coatings offer superior tensile strength, impermeability, electrical conductivity, enabling structural health monitoring, and self-cleaning properties, reducing maintenance. Nano-engineered additives improve chloride ion diffusion resistance and freeze-thaw durability, combating degradation at a microstructural scale, further extending megaproject durability. Material life cycle considerations increasingly dominate design and procurement strategies, incorporating circular economy principles, emphasizing recyclability, reuse, and environmental impacts, extending from raw material extraction through end-of-life deconstruction. Innovative cement chemistries employing carbon capture technologies embed sustainability intrinsic to materials rather than external offsets. Scaling laboratory breakthroughs to field applications presents engineering challenges, requiring rigorous quality assurance, standardized testing protocols, pilot projects, and real-world performance monitoring, ensuring reliability and safety compliance across varied climates and load regimes. Integrating advanced materials sustainably within megaprojects demands multidisciplinary synergy, uniting material science, structural engineering, chemistry, environmental science, manufacturing technology, and construction management, ensuring materials' transformative potential translates into tangible infrastructural longevity and resilience. In sum, materials innovation forms the invisible yet invincible foundation, enabling mega projects to attain unprecedented scale, efficiency, safety, and sustainability, crystallizing human ingenuity into enduring physical realities supporting generations. Logistics and construction management constitute the vital circulation system fueling mega projects, orchestrating an immense ensemble of raw materials, specialized equipment, labor, and information flows into synchronized progress amid evolving complexity. At the scales and intricacies characterizing mega projects, these functions transcend traditional project management, embodying systemic engineering challenges demanding strategic foresight, technological integration, adaptive governance, and cultural alignment to secure timely, safe, and cost-effective delivery. Supply chain orchestration underpins the continuous availability of monumental quantities of inputs: steel, cement, aggregates, electrical components, machinery, and specialized subcontractor services sourced globally. This necessitates exhaustive procurement planning, integrating supplier qualification, quality assurance, delivery sequencing, contractual rigor, and contingency frameworks, mitigating risks from geopolitical disruptions, raw material price volatility, and transportation delays. Digitally enabled supply chain management, SCM platforms employing blockchain assure provenance transparency, immutable transaction records, and contract enforcement, reducing fraud and fostering trust networks vital to complex multi-jurisdictional supply chains. Transportation logistics involve multimodal strategies, combining maritime shipping, rail transit, heavy haul trucking, and sometimes air freight, ensuring oversized, overweight components. Turbines, bridge girders, precast modules arrive within precise time windows to support labor and equipment schedules. Route surveys encompassing bridge load capacities, road geometry constraints, clearance profiles, and local regulations inform movement planning involving specialized carriers such as self-propelled modular transporters, SPMTs, capable of controlled maneuvering of loads exceeding hundreds of tons. Temporary infrastructure upgrades, such as road reinforcement or utility relocation, are often necessary to accommodate these logistical demands. Within the construction site, staging and yard management balance storage space, equipment availability, and assembly sequencing in constrained geographies, precise inventory control systems, automated material handling equipment, and just-in-time delivery models minimize on-site congestion and reduce material degradation risks. Site layout designs optimize pedestrian and vehicle flows, segregating high-risk zones, enhancing occupational safety. Workforce management is paramount, given the sheer size and diversity of labor forces, often numbering tens of thousands. Talent sourcing involves global recruitment strategies, matching skills with project phase demands from civil and structural engineering experts to specialized masons, riggers, and electricians. Scheduling systems incorporate shift rotations, skill level mapping, and regulatory compliance, ensuring operational continuity, while managing fatigue and health risks crucial for safety in hazardous environments. Multicultural training programs embed health, safety, and environmental awareness while bridging language and cultural gaps, fostering teamwork, cohesion, and morale. Digital collaboration platforms empower instantaneous communication and knowledge exchange, minimizing errors and delays. Construction sequencing engages advanced critical path methodologies, integrated with 4D BIM models, translating temporal schedules into dynamic, spatially contextualized visualizations, facilitating clash avoidance, resource leveling, and site activity coordination. Modular and prefabricated construction techniques gain prominence, optimizing quality, reducing weather dependencies, and accelerating timeline adherence, requiring highly reliable supply synchronization and dimensional precision. Risk mitigation frameworks rely on comprehensive identifying, analyzing, and monitoring strategies spanning safety, technical, financial, and environmental domains. Probabilistic modeling, including Monte Carlo simulations, evaluates schedule variations, resource uncertainties, and hazard likelihoods, quantifying risk exposure, supporting contingency budgeting and mitigation prioritization. Behavioral safety applications incorporate incident trend analyses, hazard reporting platforms, and incentive programs, fostering proactive risk-aware workplace culture. Quality assurance and control combine rigorous material testing, non-destructive evaluation techniques, ultrasonic, radiographic, thermographic imaging, and process audits, ensuring compliance with stringent design and regulatory specifications. Integrated digital quality management systems maintain traceability and generate actionable insights, reducing rework and improving safety. Environmental management integrates continuous air, noise, water quality monitoring, and biodiversity assessments, leveraging sensor arrays, feeding real-time data, analytic frameworks, dust suppression, noise attenuation structures, and water treatment facilities exemplify mitigation measures, minimizing community and ecosystem impacts. Regulatory compliance management interfaces with environmental impact monitoring, ensuring adaptive response to evolving site conditions. Technological innovations amplify logistics and construction management efficacy. IoT sensor networks track mobile equipment performance, fuel consumption, and utilization, enhancing predictive maintenance, reducing downtime. Wearables monitor worker vital signs, detecting fatigue and exposure risks, enabling emergency alerts. Autonomous vehicles and drones automate material transport and site inspection tasks, improving safety and efficiency. AI-driven analytics optimize labor deployment, equipment scheduling, and material flow forecasting, aligning with real-time conditions and project priorities. Knowledge management systems capture accumulated experience, codifying lessons learned, best practices, and operational data. Securing organizational memory, critical for megaprojects with multi-year horizons, involving changing teams and subcontractors. Financial management intertwines cash flow forecasting, milestone-linked payments, and risk-adjusted budgeting strategies supporting stakeholder confidence and ensuring uninterrupted capital supply, vital for procurement continuity and labor wage fulfillment. Contractual frameworks evolve, adopting integrated project delivery (IPD), performance-based contracting (PBC), and public-private partnership (PPP) models, realigning risk and reward structures, fostering collaboration, innovation, and rapid issue resolution. Transparent contract administration, facilitated through digital platforms, improves compliance and minimizes disputes. In synthesis, logistics and construction management's expanded scope in megaprojects represents a systemic engineering discipline, seamlessly merging technology, human factors, strategic planning, and dynamic risk management. It is the orchestral conductor transforming ambitious blueprints into functional, durable infrastructures, advancing societal progress. Risk management, insurance, and safety engineering form the critical triad safeguarding the ambition, investment, and lives intertwined in megaprojects. These extraordinarily complex endeavors inherently navigate multifaceted uncertainties, technical unknowns, environmental volatility, regulatory shifts, social dynamics, and financial flux, each possessing the capacity to escalate into catastrophes or protracted delays without meticulous anticipation, mitigation, and control. This expansive analysis illuminates the methodologies, frameworks, and innovations that coalesce to transform these uncertainties into manageable parameters, securing megaproject resilience and societal trust. The genesis of robust risk management lies in exhaustive identification and stratification of risks spanning technical, environmental, financial, social, political, and operational domains. Technical risks envelop unforeseen geotechnical anomalies disrupting earthworks or tunneling, design inadequacies, equipment failures, and construction sequencing conflicts. Environmental risks emanate from ecological degradation, invasive species introduction, pollution, and climate change-induced hazards expanding in scope and amplitude. Financial risks arise from raw material cost fluctuations, funding shortfalls, currency volatility, and contractual disputes. Social and political risks include community opposition, labor unrest, regulatory moratoria, and geopolitical instabilities, introducing layers of complexity, demanding proactive stakeholder engagement. Advanced qualitative and quantitative risk assessments utilize multimodal tools. Failure mode and effects analysis (FMEA) systematically explores subsystem vulnerability and cascading failure scenarios. Monte Carlo simulations prognosticate probabilistic range impacts on cost and schedule matrices, accommodating uncertainty distributions. Bowtie analyses synchronize hazard causes to preventive barriers and recovery controls, enhancing systemic clarity. Decision trees map dynamic evolution of interdependent risk events, enabling scenario-based contingency planning. Historic megaproject case studies supplement formal models with empirical lessons, honing detection accuracy and mitigation efficacy. Risk treatment strategies subdivide into avoidance, reduction, transfer, and acceptance. Avoidance encompasses scope modifications, removing high-risk components, or adopting less susceptible technologies. Reduction embeds redundancies in critical systems, circuit duplication, structural failsafes, extensive quality control protocols, to lower failure likelihood and impact severity. Transferring risk to third parties leverages contractual allocations, insurance instruments, project bonds, and sureties. Distributing exposure, while acceptance involves documented tolerances, managed via contingency reserves and vigilant monitoring. Insurance underwriting for megaprojects encompasses bespoke coverages tailored to unique project characteristics. Engineering and construction. All risk CIR policies insure against physical damages during design and build phases. Delay in startup DSU indemnifies income losses from schedule slippages. Third-party liability. TPL protects against environmental and bodily injury claims. Insurers demand extensive risk management documentation, site audits, and operational protocols prior to and during underwriting, ensuring alignment of risk appetites and mitigation commitment. Safety engineering permeates megaproject lifecycle stages, emphasizing prevention, detection, and response. Occupational safety and health OS/H systems deploy hazard databases, behavior-based safety frameworks, comprehensive training regimens, and incident tracking fostering risk-conscious cultures focused on proactive hazard recognition and reporting. Advanced monitoring employs wearable technologies tracking worker vital signs, environmental exposure, and location enabling real-time intervention and evacuation coordination. Automated hazard detection systems using computer vision and sensor fusion monitor equipment operation and workspace conditions, augmenting human oversight. Process safety critical in chemical, energy, nuclear megaprojects implements layered protection philosophies, inherently safer design, minimizing hazards, safety instrumented systems, employing redundant sensors, logic solvers, and actuators, executing automatic emergency shutdowns, and management of change MOC protocols, governing alteration impacts, ensuring continuity of safety. Quantitative risk assessments, QRA, calculate potential failure frequencies and consequences, guiding design and procedural enhancements. Structural safety emphasizes ultimate limit state design, incorporating seismic, wind, creep, fatigue, and impact criteria tailored to project context, employing performance-based codes. Real-time structural health monitoring, SHM systems employing fiber optic sensors, accelerometers, piezometers provide continuous data, unveiling progressive damages or destabilizations, allowing condition-based maintenance preempting failures. Emergency preparedness embeds elaborate scenario planning, encompassing fire, explosion, natural disaster, and hazardous material releases. Regular drills and virtual reality training enable stakeholder readiness, reinforcing incident command and communication protocols, optimizing resource deployment, minimizing casualties and losses. Regulatory compliance interlaces local, national, and international safety standards, including ISO 45001, OSHA regulations, and nuclear safety directives mandating rigorous auditing, third-party inspections, and reporting enforcing accountability. Cultural transformation, embedding safety as a core organizational value, transcends technical systems involving leadership commitment, worker empowerment, transparent communication, fostering trust, promoting vigilance, and continuous improvement. Financial risk management employs portfolio diversification, insurance layering, catastrophe bonds, and contractual risk allocation instruments distributing and mitigating exposure, protecting investors and operators from unforeseen shocks. Ethical considerations raise imperatives for transparency, community engagement, equitable risk distribution, and adherence to human rights, reinforcing societal license and credibility, reinforcing megaproject legitimacy. Emerging technologies in risk and safety management range from AI-driven predictive analytics, anticipating failure, precursors, blockchain securing transparent activity records, to autonomous drones executing hazardous inspections, mitigating human risk, reshaping the future of megaproject resilience. In synthesis, risk management, insurance, and safety engineering constitute intertwined, dynamic systems essential to translating visionary megaproject concepts into tangible, safe, and socially accepted realities, preserving life, property, environment, and investment integrity amid complexity and uncertainty. Financing, procurement, and contractual frameworks form the intricate financial and legal backbone, enabling megaprojects to transform grand engineering visions into operational realities. The magnitude, complexity, and long timelines of megaprojects necessitate not only colossal capital, but also sophisticated funding structures and governance mechanisms balancing risk, accountability, and stakeholder incentives. These frameworks shape how resources flow, responsibilities are allocated, disputes are resolved, and value is created sustainably across the entire infrastructure lifecycle. The staggering scale of mega-project investments, often ranging from several billion to tens of billions of dollars, requires mobilizing diversified sources of finance, blending public funding, private equity, multilateral development loans, export credit facilities, and innovative green financing instruments. Complex layered financing structures leverage domestic budgets alongside international capital markets, enabling risk distribution across governments, institutional investors, commercial banks, and project operators, sovereign guarantees, multilateral project financing, and political risk insurance mechanisms de-risk investments, especially in emerging economies or politically volatile regions. Structuring financial models requires balancing upfront capital injections against long-term revenue streams, often utilizing dedicated tolls, user fees, or availability payments under public-private partnership (PPP) frameworks, which transfer operation and maintenance responsibilities to private entities, incentivizing life cycle performance. Detailed financial modeling underpins investment decisions employing net present value (NPV), internal rate of return (IRR), sensitivity analyses, and Monte Carlo simulations assessing variations in demand forecasts, construction costs, interest rates, and regulatory conditions. Cost-benefit analyses extend beyond monetized returns, incorporating economic externalities such as environmental benefits, social inclusion, and regional development factoring into sovereign and multilateral financing decisions. Procurement strategies directly influence megaproject outcomes, necessitating approaches tailored to complexity, innovation level, and jurisdictional context. Traditional design bid build contracts may struggle with flexibility demands and knowledge integration inherent in megaprojects. Integrated methods such as design build DB, design build operate DBO, and design build finance operate DBFO shift risk and responsibilities toward contractors, incentivizing performance, innovation, and cost control. Early contractor involvement models foster collaboration, enabling constructability optimization and risk sharing. Multi-stage competitive procurement phases, expression of interest, qualification, detailed proposals ensure capable, financially stable partners aligned with project goals. Contractual frameworks embody detailed provisions carefully allocating design risk, construction hazards, cost overruns, schedule delays, unforeseen ground conditions, force majeure events, and operational performance thresholds among stakeholders. Standardized forms, including FIDIC, NSC, and bespoke international contracts, integrate performance bonds, liquidated damages, and warranty clauses safeguarding interests while fostering collaboration. Effective contract management apparatus leverage digital tools for monitoring compliance, payment certifications, change control, and claims resolution, reducing disputes and promoting timely, transparent decision-making. Payment mechanisms tie cash flows explicitly to deliverables, milestones, or performance targets, employing lump sums, cost reimbursable frameworks with guaranteed maximum prices, or hybrid models balancing incentives and cost certainty, encouraging timely execution and quality adherence. Financial penalties and bonus structures modulate contractor motivation, ensuring alignment with owner objectives. Dispute resolution frameworks prioritize alternative dispute resolution methods such as mediation and arbitration, minimizing litigation costs and preserving working relationships, crucial for prolonged, intricate mega-projects. International arbitration bodies, including ICC, SEAC, and LCIA, provide neutral forums respecting multi-jurisdictional legal harmonization. Regulatory and compliance requirements permeate procurement and financing, demanding adherence to environmental laws, labor standards, financial governance, anti-corruption statutes, and international investment treaties integrating into contractual and funding documents, assuring legal certainty and ethical conduct. Governance mechanisms in megaprojects establish multi-layered oversight, including steering committees, independent auditors, technical advisory panels, and public reporting, ensuring fiduciary responsibility, transparency, and accountability across procurement, construction, and operation phases, reinforcing stakeholder confidence and societal trust. Innovations in financing include green bonds, sustainability-linked loans, impact investment funds, and blended finance blending concessional and commercial capital, aligning investor objectives with environmental and social sustainability goals increasingly demanded by global investors and communities. Digital procurement platforms, deploying e-tendering, contract lifecycle management systems, and automated compliance controls, enhance transparency, expedite processes, and reduce opportunities for fraud or error, ensuring procedural integrity. Megaprojects spanning multiple jurisdictions navigate complexities in tax regimes, customs, labor laws, and intellectual property, requiring nuanced legal expertise and harmonized contractual provisions, ensuring consistent implementation across borders. Effective integration of financing, procurement, and contractual frameworks enables megaprojects to assemble financial resources efficiently, assign responsibilities equitably, incentivize innovation and performance, manage uncertainties prudently, and foster stakeholder collaboration underpinning functional, sustainable infrastructure delivery, despite inherent complexities. This financial and legal scaffolding transforms engineering aspirations into tangible societal assets by aligning private initiative and public interest through sound, adaptive, and transparent governance structures critical to megaproject success. Social and environmental impact management stands as a foundational pillar in the responsible execution of megaprojects, embodying the critical intersection where vast infrastructure intersects with ecosystems and societies. The inherent scale and transformative potential of megaprojects necessitate sophisticated frameworks for anticipating, mitigating, and managing complex repercussions on environmental integrity and community well-being. Addressing these dimensions requires interdisciplinary collaboration, integrating engineering with ecology, anthropology, sociology, and governance. Environmental impact assessments, EIA, are indispensable early-stage processes systematically evaluating prospective effects on air, water, soil, biodiversity, and landscape. These assessments deploy multi-pronged methodologies including remote sensing, biodiversity surveys, hydrological and atmospheric modeling, and socioeconomic analyses, identifying sensitive habitats, species at risk, water quality parameters, and community resource dependencies. Impact prediction integrates spatial temporal modeling, forecasting pollutant dispersion, habitat fragmentation, and carbon emissions informed by construction and operational scenarios. These data inform design alternatives, minimizing environmental footprints through siting optimization, low-impact construction techniques, and ecosystem restoration commitments. Biodiversity conservation within megaproject contexts employs innovative strategies extending beyond regulatory compliance toward integrated landscape-scale planning, creation of wildlife corridors, reforestation, wetland mitigation, and adaptive management guided by ecological monitoring programs support habitat connectivity, offsetting unavoidable disturbances. Emerging approaches incorporate ecosystem services, valuation embedding the economic and social benefits of healthy ecosystems into project cost-benefit analyses, ensuring conservation decisions align with broader human well-being objectives. Water resource management integrates careful stewardship of surface and groundwater systems to mitigate contamination, depletion, or altered flow regimes. Mitigation measures include sedimentation basins, bioretention swales, constructed wetlands, and advanced wastewater treatment technologies, reducing pollutant loads, retaining water quality for downstream users and aquatic life. Dynamic modeling assesses hydrological impacts, accommodating climate change-induced variability, supporting adaptive reservoir operations and robust flood risk management. Air quality management involves dust suppression systems, machinery emissions controls, and monitoring networks ensuring compliance with stringent standards protecting human health. Noise attenuation employs barriers, scheduling restrictions, and machinery insulation, minimizing community disturbances. Fostering social license. Social impact assessments encompass demographic profiling, cultural heritage preservation evaluations, livelihood impact analyses, and health risk assessments. Participatory approaches engage affected communities through inclusive consultation frameworks, embedding local knowledge, aspirations, and concerns into project decision-making, enhancing legitimacy, and minimizing conflicts. Compensation and resettlement programs adhere to international safeguards, ensuring fair, timely, and culturally sensitive relocation and livelihood restoration, supporting social equity. Community engagement strategies employ multi-channel communication, public hearings, workshops, digital platforms, ensuring transparency and iterative dialogue with stakeholder groups, fostering trust and collaborative problem solving. Grievance redressal mechanisms provide accessible forums, addressing concerns swiftly preventing escalation. Health and safety management extends beyond workers, ensuring community protection through emergency preparedness plans, addressing potential incidents, including construction accidents, hazardous materials release, or natural disasters. Collaboration with local authorities enhances response capacities, improving resilience. Climate change adaptation and mitigation permeate impact management, integrating greenhouse gas reduction targets, renewable energy integration and design adjustments, accommodating projected climatic shifts, securing project longevity. Sustainability frameworks such as the International Finance Corporation, IFC performance standards, UN Sustainable Development Goals, SDGs, and ISO 14001 operationalize environmental and social governance, embedding accountability and continuous improvement into megaproject life cycles. Monitoring and evaluation systems combine sensor technologies, satellite imagery, field inspections, and community-based reporting, enabling adaptive management, dynamically addressing emergent issues, ensuring compliance, and fostering mutual accountability. Economic valuations incorporate externality, pricing embedding environmental and social costs within financial analyses, aligning investment decisions with sustainability imperatives. Ethical stewardship underpins impact management, promoting procedural justice, equitable participation, distributive justice, fair benefit sharing, and recognition justice, respect for cultural identities and indigenous rights, affirming megaprojects as agents of inclusive development. Risk-informed decision frameworks balance development benefits against unavoidable impacts, employing transparent trade-off analyses supported by multidisciplinary expertise. Innovations such as nature-based solutions, NBS leverage ecosystem restoration, enhancing climate resilience, while environmental DNA, eDNA, monitoring offers non-invasive biodiversity assessments, revolutionizing impact tracking. In conclusion, social and environmental impact management elevates megaproject engineering into an integrated stewardship paradigm, ensuring that monumental infrastructure advances coexist harmoniously with vibrant ecosystems and flourishing communities, securing enduring legacies defined by sustainability, equity, and shared prosperity. Safety engineering and monitoring embody the critical guardianship of megaprojects, transforming vast, intricate construction zones and operational systems into controlled environments where human life, asset integrity, and environmental protection are prioritized without compromise. This domain represents a nexus where technology, organizational systems, human factors, and culture coalesce, devising anticipatory, adaptive, and resilient frameworks, safeguarding multifaceted infrastructures conceived and executed at previously unattainable magnitudes. A foundational pillar of megaproject safety is the comprehensively applied Health, Safety, and Environment HSE management system. These systems institutionalize hazard identification, risk assessment, and mitigation strategies, encompassing physical, chemical, biological, and psychosocial domains intrinsic to large-scale construction and operations. They enforce hierarchies of controls beginning with hazard elimination, substitution, engineering controls, such as guardrails, ventilation systems, and noise dampening, followed by administrative protocols and personal protective equipment, PPE selection, tailored to distinct worksite environments and exposure risks. Emerging sensor networks tethered to the Internet of Things, IoT, revolutionize real-time exposure monitoring. Sophisticated arrays embedded within construction zones continuously sample airflow composition, particulate levels, temperature, and noise, alerting supervisors and workers rapidly to unsafe conditions. Wearable devices enhance safety through biometric data collection, measuring heart rate variability, skin temperature, and motion patterns, identifying fatigue, heat stress, or falls, thereby enabling preventative interventions, increasing survival and productivity. Structural and equipment health are vigilantly monitored by integrated structural health monitoring, SHM systems, employing fiber optic strain sensors, accelerometers, and ultrasound scanning embedded within critical components. These continuous data streams feed centralized platforms equipped with machine learning algorithms, separating normal operational fluctuations from early-stage anomalies, such as crack propagation or corrosion hotspots. This proactive visibility reduces catastrophic failures through condition-based maintenance, impacting cost-effectiveness and life cycle extension. Robotics and unmanned systems assume pivotal roles in hazard zones. Traditionally inaccessible or perilous for humans, multifunctional drones execute high-definition aerial site inspections, identifying safety infractions, equipment degradation, and environmental nonconformities, with repeatability and speed unattainable by manual inspection. Autonomous ground vehicles transport materials through congested workyards, minimizing collision risks. Robotic exoskeletons worn by workers augment strength and reduce musculoskeletal injury risks during repetitive or heavy lifting tasks. Emergency preparedness manifests through elaborated all-hazard contingency planning, integrating scenario-specific response strategies to fires, chemical spills, structural collapses, natural disasters, and health emergencies. Virtual reality, VR, and augmented reality, AR immersive training platforms, simulate emergency conditions, enabling personnel to develop situational awareness, decision-making skills, and rapid response competence in safe, controlled settings, reducing training accident risks and improving retention. Cyber-physical safety integrates supervisory control and data acquisition SCADA systems with embedded safety instrumented systems, SES and programmable logic controllers, PLCs, implementing fail-safe operational limits, emergency shutdown protocols, and real-time diagnostics preventing machinery malfunctions and cascading systemic failures. Redundancy through hardware diversity and software fault tolerance ensures operational continuity, pertinent to critical infrastructure, with no tolerance for downtime. Organizational safety culture permeates megaprojects, profoundly influencing adherence to protocols, incident reporting, and continuous improvement. Leadership commitment, actively modeling safety behavior, cascades through all levels. Behavioral-based safety programs incentivize hazard recognition and mitigation, empowering workers as proactive safety stewards. Transparent, blame-free reporting environments cultivate trust essential to early problem detection. Psychosocial workplace health initiatives address stress, fatigue, and mental health risks inherent in high-pressure, extended shift environments typical of megaproject sites. Programs provide counseling, peer support, fatigue management, scheduling, and workload adjustments, enhancing workforce resilience and reducing accidents linked to human factors. Regulatory frameworks around the world mandate systematic certification and auditing, incorporating ISO 45001 occupational health and safety management systems, and other local authorities, ensuring statutory compliance and alignment with international best practices. These regulatory obligations intensify on high-profile projects given societal expectations and legal liabilities. Performance measurement uses leading and lagging indicators, evaluating near misses, incident rates, proportion of hazard assessments completed, and safety audit results, informing continuous monitoring. Advanced analytics distill data trends directing resource allocation, optimizing intervention effectiveness. Financially, investment in safety reduces direct costs related to accidents, medical expenses, compensation claims, equipment repair, and indirect costs including schedule delays, reputation damage, and contract penalties, creating compelling business cases, reinforcing safety as a strategic imperative. Innovative frontiers explore predictive safety analytics, applying big data, combining environmental variables, worker behavior patterns, and equipment status forecasting. Hazard emergence enabling preemptive correction, transforming safety from reactive to predictive discipline. Ultimately, safety engineering and monitoring in megaprojects manifest a multi-dimensional architecture employing state-of-the-art technology, organizational excellence, and human-centered design, ensuring that engineering grandeur never comes at the expense of life, health, or ecological harmony. This relentless stewardship fortifies the human endeavor of megaproject construction and operation, guaranteeing that monumental infrastructure stands robust, not only in form and function but within the paramount mandate of safeguarding people and planet.